As we have seen in the introduction video, connecting an intermittent power supply, such as PV, to the grid will cause some issues. The issues can be divided into voltage issues, power issues, and frequency issues. In this video, I will discuss how adding PV to a grid can affect the voltage. This will include voltage fluctuations, grid-derived voltage fluctuations, voltage imbalance, voltage rise, and reverse power flow. One of the first problems that can occur with intermittent power supplies, such as photovoltaics, is voltage fluctuation. In traditional power systems, there is a constant power supply from the power source that can be programmed to match the demand. The power source operates at a constant, high voltage. The generated power is delivered to the transmission system and eventually distributed to the consumers at a lower voltage level. On the other hand, in distributed generation technologies like photovoltaics, the power output is more variable and impossible to control. This can cause overvoltage or voltage dip situations in the low voltage distribution system, which can have effects on the performance of different loads. Effects on the loads are usually noticed when the voltage fluctuates more than 10% above or below the nominal voltage. In grid-connected systems, voltage fluctuations may occur also outside of the PV system, depending on the stability of the grid. In this case, we want to preserve our PV system from damage by means of some safety mechanisms. A PV system connected to an inverter is providing power to the low-level distribution grid. No problems occur when the voltage of the grid is constant and at a nominal value. However, some fluctuations may also occur at the distribution level, causing an overvoltage at the inverter. In these situations, inverters normally feature a disconnecting system that is set to avoid the grid-derived voltage fluctuations that may be transmitted to the PV system. If the voltage of the grid is higher or lower than a preset threshold, the disconnector will shut off the PV system from the grid. This means that the PV power generated during this period of grid's instability will be wasted. One way to broaden voltage dip tolerances is to incorporate low voltage ride-through, or LVRT, techniques into the inverter design. This term refers to the capability of electric generators to stay connected in short periods of lower electric network voltage or voltage dip. When the voltage of the distribution system goes down, the inverter is programmed to keep injecting current into the system. This way, the PV is able to remain connected to the grid for short period voltage dips or brownouts. Without LVRT, a small grid fluctuation would then cause the PV to shut off. This in turn would cause a greater voltage dip, which would result in a cascading failure. Such a failure may result in a major blackout, so LVRT protection is essential to keeping grids healthy. Voltage imbalance may be a problem for the system stability. To visualize a three-phase voltage system, we need a time domain and a voltage domain, in which sinusoidal voltage can be drawn. A single-phase system is composed of one sinusoid, and in the three-phase system, we have also a second and a third signal with a phase difference of 120 degrees between each phase. Problems will occur if the phase difference changes to a value other than 120 degrees. Also, when the amplitude of the voltage is not the same for all the phases, imbalances can occur. So, if a single-phase generation gets distributed in the three-phase system, this can lead to an imbalance that will have a negative impact on small distributed generators, such as temperature rise of the rotors, noise, and vibration. Generally, the difference between the highest and the lowest voltage should not exceed 4% of the lowest voltage. Single-phase PV systems installed disproportionately on one of the three phases may cause severely unbalanced networks. Damages to control systems and damages to transformers can also occur. This is the reason why at high PV penetrations, the cumulative size of all systems connected to each phase should be as equal as possible. Generally, all systems with installed power above 5 kilowatt peak should be connected to an inverter which can guarantee a balanced three-phase output. Typically, in traditional systems, power plants provide power at 400 kilovolts, which is sent to transmission lines at 50 to 150 kilovolts through step-down transformers. Switchgear substations at around 10 kilovolts are used to redirect the power to either low-voltage distribution grids or factories. Large factories require higher voltage level and higher system reliability. In the last step, households receive power at 220 volts. This is the voltage level that we receive it every day in our sockets in Europe. When a house starts generating power at a different voltage level by means of PV systems, problems can arise. The linearity of the traditional system is now changed into a decentralized and bidirectional distribution system. In this distribution system, PV systems provide power at low voltage to the substation. Storage systems may be necessary when PV penetration on the grid is high. Bigger solar and wind farms play also a role at the transmission level. In this more complicated scenario, protection devices on the low voltage side of the network are designed to detect and stop upstream current flow towards the transformer. If distributed generation systems result in a reverse power flow through the regulator, tap changing control systems in the transformer which regulate the turn ratio and therefore the voltage inputs and outputs may become unstable. Distributed generation reduces grid reliability if care is not taken in the design of tap changing to handle downstream and upstream current flows. This is the biggest challenge when designing new electricity grids like smart grids that can guarantee control over complex power flows given by distributed generation such as PV. So, to sum up, in this lecture we went through the concept of voltage fluctuations and how these affect grid and load performance. We learned how the grid can affect PV system performance when a voltage dip occurs. We also discussed voltage imbalances and how a PV system should be connected in order to avoid this problem. Finally, we saw the effects of voltage rises and reverse power flows on the power grid. In the next video, we will continue our discussion of grid integration with the power issues.